Hello there, and thank you for joining me today in this lesson about sine, cosine, and tangent. Our objectives today are to solve for side lengths and angles within right triangles with the understanding that the Pythagorean theorem, although usable with right triangles, is not going to help us today. So sine, cosine, and tangent, what are they? They are ratios. They are fractions. Specifically, ratios we get when we compare various sides of a right triangle relative to a given angle. Here's an example, right? There are lots of applications where, let's say we have a 55-degree angle over here. It would be helpful for us to know, hey, if this angle is 55, when we compare this opposite side to the hypotenuse in this diagram, okay, what fraction, what ratio do we get? And regardless of whether this triangle is, scaled up or down, as long as that's a 55-degree angle within a right triangle, that ratio is going to be consistent, okay? There are three trigonometric ratios we concern ourselves with here. They are sine, cosine, and tangent. Sometimes math students and teachers memorize those ratios with the saying on the screen there, SOHCAHTOA. The ratio sine for a given angle theta, this is the Greek letter theta, compares the opposite side of that angle to the hypotenuse of the triangle. And everything is relative to the angle in question here, opposite side and hypotenuse. Cosine compares the adjacent side to the hypotenuse, and tangent compares the opposite side to the adjacent side. SOHCAHTOA, sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. Okay, again, the thinking is, for whatever angle, whether it's 55 degrees or 42 degrees, if we draw in a triangle to model that, whether we scale that triangle up or shrink it down, when we compare these various sides, we get the same ratio every single time for that given angle theta. We're going to use it to solve for some missing side lengths and some missing angles, but first we've got to practice with this terminology of opposite, adjacent, and hypotenuse. And to do so, we'll just take a right triangle and practice writing in some of these trigonometric ratios. Okay, we'll just do one of these to keep the video a little bit more brief. Consider the blue triangle off to the left here, and this is a right triangle. It says find the values of sine, cosine, and tangent for the given angle. The given angle is the angle with the Greek letter theta in it. In order to do this correctly and identify those ratios, we've got to identify the opposite side, the adjacent side, and the hypotenuse. Well, regardless of whatever angle we're working with here, the hypotenuse is what it is. It's the longest side in this right triangle. It's the side that is opposite the 90-degree angle. And so the hypotenuse in this situation is 17. Now, relative to this angle theta, 15 would be considered the opposite side, like across from. Like you've got your back to the corner here and you're staring out this way. You're looking at the opposite side, the opposite wall. That's 15 relative to this angle theta. 8 would be considered the adjacent side. Think of adjacent as next to the angle in question here. Now, the opposite and adjacent sides would switch if we were considering this angle up here. Now, all of a sudden, the opposite side is 8 and the adjacent side is 15. So we've got to keep everything relative to the angle in question. Now that we've identified those three sides, let's fill in our ratios here. Sine, S-O-H, is opposite over hypotenuse. And the side opposite theta here is 15, and the hypotenuse is 17. So whatever this angle theta is, the sine ratio for that angle is 15 over 17. Cosine is adjacent over hypotenuse, and for the angle theta here, that's 8 over 17. Tangent is opposite over adjacent. Opposite is 15, adjacent is 8, so we end with 15 over 8 here. There's nothing magical going on with this exercise, just practicing that terminology of opposite, adjacent, and hypotenuse. Now the goal, remember, today is to solve for missing side lengths and missing angles. And there are going to be times where we work with some angles whose sine, cosine, and tangent ratios aren't, nice rational numbers or even irrational numbers that can be expressed with, simple square roots like square root 3 and square root 2. In other words, there'll be times where we have to use our calculator. And so grab whatever calculator you plan on using, whether it's a handheld scientific calculator or perhaps like the Desmos calculator we like to use in class. But let's practice evaluating sine, cosine, and tangent. Almost all handheld scientific calculators will have dedicated buttons for these three trig ratios. If you're using the Desmos calculator, if you tap on the functions button, you can choose from the list. Otherwise, you can just type in COSSINTAN. But practice with your calculator here. If you want to pause and try first, then check your answers. That would make sense. Otherwise, we can just roll through it here. So when you calculate cosine of 22 degrees, and if we round that to 2 decimal places, we should get 0.93. If you feel like you typed in exactly cosine of 22 and you got a different answer, check to make sure that your calculator of choice is set to degree mode. It may be set to radian mode, and we'll talk about radians in a later chapter. But these are the answers I have when calculating these three using a calculator. Notice that cosine and sine give us values less than 1. We'll talk more about that in the next chapter. Tangent gives us a number quite larger than 1, and we can talk about that in the next chapter as well. But this was just some basic calculator practice so that we can move on now to the next step. So let's move on to the next step today, where we finally get to our first objective, and that is to solve for missing sides in right triangles. Previously, we've discussed the Pythagorean theorem and some patterns for special right triangles. Neither of those techniques will help us here, though, because we don't have special right triangles, like 30, 60, 90, or 45, 45, 90. And also, to use the Pythagorean theorem effectively, we need to know 2 of the sides, and in these situations, we only know 1 of them. Let's try this blue triangle first. We're given a 34-degree angle, and relative to that 34-degree angle, we are given the opposite side. And we want to know x, which is the hypotenuse. The idea here is to set up an equation using one of our 3 trig ratios. And of those 3 trig ratios, we should probably use the one that deals with opposite and hypotenuse. Well, if you go back and take a look, or perhaps you have them memorized, the trig ratio that deals with opposite and hypotenuse is sine. So here's the setup here. We would say sine of this 34-degree angle would be equal to the opposite side, which is 15, over the hypotenuse, which is that x we're trying to solve for. So there's the setup. Let's talk about solving for x now. Currently, x is trapped in the denominator of that fraction on the right-hand side. So to get it out of that denominator, let's multiply by x on both sides. So now we have x times sine of 34 degrees equaling 15. Don't let that sine of 34 degrees intimidate you or throw you off your game here. Let's stick to our equation solving principles. Currently, we have x times a number equals 15, because after all, sine of 34 degrees is a number. It's going to be some decimal, but it's still a number. So to finish solving for x, we should divide both sides by that number. And I don't really need to know exactly what sine of 34 degrees is right here. I just have to take 15 and divide by it. So that's exactly what I would type into my calculator, making sure I close my parentheses around this 34, making sure I'm still set to degree mode. But when I take 15 and divide by sine of 34, and I think we'll round to 2 decimal places here, we'll get 26.82. Is there a unit provided? There is not. So we can just call our answer what it is. This problem dealt with sine. Not every problem will do so, so let's try something slightly different. Here, relative to this 57-degree angle, x is the opposite side, 32 is the adjacent side. The trig ratio that deals with opposite and adjacent is tangent. So our setup would be tangent of 57 degrees equals the opposite side x over the adjacent side 32. This time, x is not stuck in the denominator, so we can approach this a little bit differently. Currently, x is being divided by 32, so to get x by itself, let's do the inverse operation. Let's multiply by 32 on both sides. So the expression I'll need to type into my calculator is 32 times tangent of 57 degrees. When we do that and round to 2 decimal places, I'm seeing 49.28. Quick side note here, we used tangent because we wanted the opposite side and we were given the adjacent side. We could flip the perspective on this potentially, right? If we know that this angle is 57 and this is 90, collectively those add up to what? 147? And if those add up to 147, then this has to be a 33-degree angle, right? All the angles have to add up to 180. Okay, so if we wanted to, we can now approach it from this 33-degree angle. I guess we'd still be using tangent, though. It would just be tangent of 33 equaling now the opposite side 32 over the adjacent side x. I don't know why we would choose to do that because it introduces more work, but just something I wanted to point out. So here are 2 examples where we can solve for side lengths using sine, cosine, and tangent. We didn't have a cosine example here, but that's what the extra practice is for. We're going to jump ahead to try to keep this video as brief as possible here. So moving on to objective number 2 now, we can also use sine, cosine, and tangent to solve for angles within right triangles. Now, we just got done using sine, cosine, and tangent to solve for side lengths. Okay, and the setup of our equation was, sine of an angle gave us a ratio. Well, if we know the ratio and we want to get the angle, we're going to have to do that backwards. In other words, we're going to have to use the inverse of sine, cosine, or tangent potentially. And there are usually dedicated buttons for these functions. On a handheld scientific calculator, they might be the second function for the sine, cosine, and tangent buttons. If you're using the Desmos calculator and you tap on the functions button, scroll through enough and you'll find buttons for inverse. You can see that inverse notation with that -1. But our next step, we'll have to evaluate expressions like the ones we see on the screen. So if you want to pause and get that calculator practice right now, you could. Try evaluating inverse sine of 1/2 and the rest of the examples here, and I'll write down the answers in a moment. Inverse sine of 1/2 is exactly 30 degrees. I'm using the degree symbol here deliberately. With inverse trig functions, the inverses are the ratios, or the inputs are the ratios, and the outputs are the angles or the degrees. Okay, inverse cosine of 0.893 ends up about 26.7 degrees. Inverse tangent of -0.234 gives us a negative result, which was kind of curious, right? We'll talk more about negative angles in the next chapter. If you feel like you typed in exactly this and you didn't get the same things, again, check that your calculator is set to degree mode. That might solve the issue. So, let's finish our lesson here. Solve for the missing angle in each triangle, round to the nearest hundredth if necessary. Let's try this one here. We've got this right triangle trying to solve for angle x. Pythagorean theorem doesn't help us to solve for angles, right? So that's out. The special right triangle relationships won't help us to solve for angles, so that's out. It's truly sine, cosine, and tangent, and I guess they're inverses that will help us out here. But here's the setup. Relative to the angle x that we're trying to solve for, 12 is the opposite side, and in this right triangle, 13 is the hypotenuse. So like we did earlier today, we should use the trigonometric ratio that deals with opposite and hypotenuse, and that ratio is sine. So our setup looks like this. Sine of x degrees will be the opposite side, 12, over the hypotenuse, 13. Now, the solving here is different, though, because x, the angle we're trying to solve for, is trapped inside of this trig function, this sine function. We need some way to break it out of that sine function. We need an inverse operation, basically, right? Think about having something like x squared equals 50. We want to solve for x, we do the inverse operation. We take the square root to both sides. Well, as it turns out, there is an inverse operation, an inverse function for sine, and it is named inverse sine, sometimes referred to as arc sine. Here I'm using that inverse notation with that -1 exponent. But applying inverse sine to both sides is going to free up that variable x. And so x will equal whatever inverse sine of 12 divided by 13 equals. And we just practiced typing that into a calculator, so that's what I would do at this point. And let's round these angles to the nearest tenth, and if I punched it in correctly, I'm looking at 67.4 degrees. So we solve for angles in right triangles by ultimately using inverse sine, inverse cosine, or inverse tangent. To keep this video as brief as possible, I think we'll skip ahead and wrap things up. You would get practice with these word problems by doing the associated homework assignment. So that's enough right now about sine, cosine, and tangent. We use them to solve for missing sides and missing angles in right triangles. Thank you for watching.